Okay, so welcome to our favorite 1.5 hours of the week, to our bi-weekly seminar. We have a double act today. So some people struggle with inflation. Here you get 2 for the price of 1 today. So we have Stefan and Raffaela, both from Ulm and both working on model transformations, essentially illuminating 2 different aspects here, one more on the sort of general evaluation of model transformations and their advantages and disadvantages, and the other one specifically on performance. So I'm looking forward to hearing sort of lots of new ideas and possibly challenges that we can all address then later. So please, Stefan, do you want to start?
Yes, thank you very much, Raiko. And thank you to the organizers for the opportunity to present our work here today. So as Raiko already said, today I'll be talking about the evaluation of model transformation languages, or better, the evaluation of certain advantages and disadvantages of model transformation languages. Specifically, I want to talk about 2 empirical studies that we did to investigate whether there are advantages and disadvantages and what those advantages or disadvantages are. Before we go into the actual research, just some basic background. Within the model-driven software engineering, model transformations play an essential part within this framework, and model transformation languages have been introduced to kind of help developing those model transformations. And the specificity of these languages intuitively makes them better for defining model transformations than doing the same thing in general purpose languages. This intuition is also reflected in literature with many claims. If you read papers that state things like it's easier to write model transformations with a model transformation language, it's easier to read those, they're faster, and Raffaela will talk about that later, and also they're way more analyzable than general purpose languages are. However, we have one problem with all these claims in literature, and that's the fact that there's little to no substantiation for a large portion of those claims. Yeah? We can easily exemplify this if you just take a publication, maybe one you want to read in the next few weeks, or a publication you read the last few days. Take the publication and better take a publication that talks about model transformation languages or introduces a new model transformation language, and read it. Then try to figure out how many claims about model transformation languages are made within this publication. So what does the publication state about model transformation languages? And then check how many of those claims are actually substantiated within the paper. Yeah, what you most likely will see is that there's a lot of statements within the publication about certain advantages or maybe drawbacks that are not substantiated in any way. Now, this doesn't necessarily have to be bad, right? There are things that you don't need to substantiate every time you talk about it, like the mathematicians won't prove that 1 + 1 = 2 in each paper, because that's not necessary anymore. But it's pretty unsettling that there's that many claims in literature that seem to have no substantiation. And this is where our first portion of our research comes in. So the basic structure of what I've talked about already right now is what we did on a large scale in a structured literature review. In this literature review, we searched through 4 different literature search engines and filtered through around 4,000 publications, from which we selected a total of 58 publications which fit our selection criteria, and extracted from those all the claims about model transformation languages that were made in the publications, as well as all evidence and substantiations that were presented within the publications. In the following minutes, I'll go over the results of this study before then presenting an additional empirical study where we tried to provide some more empirical evidence for a certain subset of all the claims that we found. Okay, let's first start with the claims. Here's a list of some of the claims that we found in the 58 publications. It's not complete since they didn't fit on one slide, at least not properly, because in total we found we found exactly 137 claims about model transformation languages. And these claims differ greatly. So some are concerned with theoretical expressiveness of model transformation languages. Some are related to comprehensibility, some are related to performance, some to tool support, and so on. There's a total, we found a total of 15 different properties that are being discussed in literature. And these claims also differ greatly in the specificity and in their specificity and how or if they provide any substantiation for the claim. Here's a few examples. First, we have this claim that general purpose languages lack suitable abstractions for specifying model transformations. Well, the problem with this claim is that it's pretty broad, right? It talks about all general purpose languages. And thus, that's pretty easy to attack with just one counterexample of any general purpose language that has some sort of abstractions for model transformations, right? Another problem that we've seen several times is highlighted by this example. This claim is that they use a model transformation language because model transformation languages are easier to understand. Here, the problem is that the claim is just there to justify the usage of a model transformation language without any substantiation whether this claim actually holds or not. This again puts the work that's being presented on some shaky ground from the beginning, since, well, we can't be sure that that's actually all that is there for it. There's also another set of claims that I want to highlight, and that's opposing claims. So here we have two sets of claims, basically. One set of claims is that model transformation languages are more performant for transforming models than general purpose languages. And we have a different set of claims that talk about the fact that the performance is one of the shortcomings of model transformation languages, which hinder their wider adoption. The problem here is not that only one of both statements could be true, but that it highlights that there's a need for proper contextualization of statements of this fashion, right? So in some cases, maybe model transformation languages are more performant. In some other cases, they might not be. And it's difficult to discuss the performance without giving much context to go from. Of course, there's also claims that give proper substantiation, that provide proof, that provide evidence, that discuss the context in great detail. But sadly, those claims are in the minority of the claims that we found. So talking about substantiation, let's move on to that. We found 4 different types of evidence that is provided in literature to kind of substantiate claims that are made about model transformation languages. The first type of evidence that is sometimes provided is evidence based on empirical studies. So either a claim is made as a result of an empirical study, or a claim is the subject of an empirical study and is then therefore evidently proven or disproven, maybe. The second type of evidence that is provided are citations. So the basic principle of a claim is stated and then is accompanied by a citation of different literature for providing context or evidence for the stated claim. The third type of evidence that we found was experience or examples, meaning the authors of a publication relied on either their experience or on examples to kind of provide explanation as to why they believe that certain properties hold. The fourth type of evidence is the type of evidence where actually no evidence is given. Okay. This doesn't, I talked about that earlier, this doesn't necessarily need to be a bad thing, since some things don't need to be substantiated every time, but maybe not as many as we found. Overall, all these different types of evidence have different implications as to what they really say about a claim that is substantiated by them. And this is what I'm going to talk about in the next few minutes. Okay, first up, empirical studies. Empirical studies are generally great. They provide evidence and substantiation for whatever subject we're trying to investigate. And they also provide context. So they provide the context that is necessary to understand when these claims actually hold and when they might not hold because the empirical study didn't cover that or something like that. There is, however, one major problem with empirical studies and empirical evidence for model transformation languages, and that's the fact that there's very little of it. So we only found about 9% of claims, or 9% of all the claims that we found had empirical evidence associated with them. So either the claim was stated within the publication as a result of the study, or it was the subject under consideration. Moreover, of the 58 publications that we considered, only 4 were empirical studies. So there's a sort of mismatch between the foundation research and the empirical research to try and underline the research. Okay, moving on to citations. Citations are a core principle in research to provide context and substantiation for statements. And thus, it should be a great way to provide substantiation for your claims in and around model transformation languages. There are, however, 2 problems that we found in some of the publications that used citations to kind of substantiate their claims. For one, some citations pointed towards publications that didn't provide any substantiations themselves. So it was more of a referral to another group of people that were of the same opinion as the authors of the first publication. The other problem is related to the closeness of the cited publication and the context of the content of the cited publication to the publication that cited it. We had some examples for where a publication about model transformation languages that stated some claims about them pointed towards publications about domain-specific languages. And that's, again, a problem, that a point where there isn't necessarily a problem if you properly discuss the fact that the substantiation that you're trying to point to isn't directly about model transformation languages, but more for the general aspect of domain-specific languages, for example. Next up, experience and examples. First, experience. Experience is very relevant for providing confidence in anything, basically. You just have to look at expert opinions for cost estimation in software projects. The experts are often referred to when trying to estimate how long or how costly your software project will be. However, the problem with expert opinions in this case is that they can sometimes be hard to argue outside of the community or the group you're in, because for an outsider, it's hard to get a feel of how much this expert really has experience, or also to even get a feel for the general community and how well experience within the community really works. Examples, on the other hand, are great for illustrating specific properties, right? With one example, you can directly show one specific property, but they are very limited in their ability or in their applicability to the general case, because as there are examples, they generally tend to only be applicable to the one example that you show. This, again, doesn't necessarily have to be a problem, but it needs to be properly discussed and properly presented as to not lead readers to believe things that might not actually be true. Lastly, the evidence type, or the type of claims where no evidence was given. This is generally bad, right? Because if there's no evidence, it's easy to disagree, and it's hard to defend your position without any evidence. I've talked about the fact that this isn't always the case, since there might be a general consensus on what's generally accepted, like 1 + 1 = 2 in maths, for example. However, at least we didn't find any research that you could point to that outlines any sort of consensus that exists within the model transformation language community, which again makes it hard to argue many of the claims that are stated to people outside of the community, because there's no way to point them to any starting point. You can just say, we as a general, in general in the community believe that's the case, but well, that could be biased due to some conflicts of interest or stuff like that. Another problem is the overwhelming amount of claims that are stated without any accompanying evidence. Well, even if we cut a part out for the claims that are generally accepted, we still have maybe half of all claims that are not substantiated in any way, which kind of points to a gap within the research that's being done right now. Okay, now that we've identified this gap, that more research needs to be done into providing evidence for claimed advantages or disadvantages of model transformation languages, we tried to combat that by starting to work in that direction ourselves. We've selected a number of claims. Here are 2 examples of those claims. The first one you already know: general purpose languages lack suitable abstractions for specifying transformations. And the second example, model transformation languages can hide transformation complexity and burden from the user. So the gist of all these claims that we selected for our study is that it's easier to express model transformations when using a model transformation language compared to when using a general purpose language. And our intention now was to provide more empirical evidence for or against this set of claims. Okay, now the idea behind our study was to take a model transformation language and a general purpose language and compare the transformations written in both languages with each other, to see kind of if there's abstractions, or how abstractions or the structure of the model transformation language impacts the final code. Since many of the claims about model transformation languages actually originated 15 to 20 years ago, we also wanted to do kind of an historical perspective on this whole thing, and wanted to look at the difference between using a more current general purpose language as opposed to a older version of the general purpose language, when maybe model transformation languages were first introduced. Now, as representatives for our model transformation language and general purpose language, we chose ATL and Java as two prominent languages of their respective types. And for the different versions of our general purpose language, we decided on using Java 14 as the latest stable version of Java when we started our study, and Java 5 as the latest stable Java version when ATL was first introduced. Now, what we wanted to do during the comparison was, when comparing the general purpose language with the model transformation language, we wanted to look at the distribution of effort that needs to be put into the Java code or the ATL code to make the transformation work. And when we compare ATL, Java with the different versions, we wanted to look at the complexity of the code and how that changed over time, and maybe also look at the size and how that changed. Now, the ways we tried to measure these two things was, for the comparison of ATL and Java, we looked at a word count measure that counted the words in both languages, attributed the amount of words for each language with different aspects of the transformation, and compared how much words are required in which language, as well as some general manual code inspections where we just compared the code with each other. Then on the side of the comparison between Java, we relied on the line of code measure or the lines of code measure, again, the word count measure for different size measure, as well as the McCabe complexity for measuring the complexity of the Java transformations. Now, to achieve the goal of our study, we planned to take a number of already existing ATL transformations and translate those into Java, both Java 5 and Java 14, and then analyze the resulting transformation scripts in both languages based on the measures and proceedings that I presented on the last slide. Okay, coming to the results first, the advancements Java made over the years. Here's a figure that depicts the sum of all McCabe complexities of all transformation scripts written in Java on the left-hand side for Java 14, on the right-hand side for Java 5. And this figure differentiates the complexities based on what transformation aspect is implemented in the corresponding code behind the complexity. This figure, in essence, shows two things. For one, the newer Java version helps in reducing the complexity of our Java code by a lot, by about 50%. So newer Java versions seem to really help in reducing the complexity of your written model transformations. And the other thing that it shows, and that's less of a good thing, is if we look at the actual code and look at the distribution of the code between the actual transformation and any sort of extra code that we need to write so that the transformation actually works, there's no real change between the Java versions. So around and about 57% of the complexity, both in Java 5 and in Java 14, are code that actually transform things, whereas all the rest is overhead that's just there and doesn't really contribute to the actual transformation in and of itself. The largest overhead nowadays is, by the way, trace management, one of the huge selling points of languages like ATL, for example, since they can abstract that away. Moving away from complexity towards the size comparisons in Java that we made, we found that the size, when measured in lines of code, is greatly reduced between Java 5 and Java 14. So we now need a lot less lines of code to write our Java transformations. However, when we look at the word count, there's no real change there. So that basically means while newer Java versions help in reduce the size or the length of your code, they do so by compressing the amount of words into less lines of code, meaning you have a more word-dense code nowadays. Also, some things that we observed when looking at the code themselves was there's a way less explicit control flow that you need to define in Java 14 if you want to than what was necessary in Java 5, which points towards the ability to define a more data-driven kind of transformation in Java nowadays. Okay, moving on to the comparison between Java and ATL. You've already seen this figure, and I've already talked about some of the implications, but I want to highlight again this overhead code. ATL, all this code that's highlighted here, all the complexity of the code associated with model traversal and tracing are things that ATL abstracts away from completely. So we don't need to write tracing, we don't need to write traversal, we don't really need any setup code to read the models and to write the models, which in essence means that 40 to 45% of the total complexity within our Java code is associated with basically unnecessary code or code that could be abstracted away from if you used a model transformation language. Moreover, ATL does so with less words. Yeah. So comparing the word count between ATL and Java, you can see that ATL only requires about half as many words to achieve the same goal. And even if you strip away all the overhead code in Java and just look at the transformation code, then there's still more words required in Java than in ATL, even if you abstracted away all the other things. Another thing that we observed by just analyzing the code, so looking at it and comparing it with each other is, and many of you probably know this already, ATL forces a strict structure on developers when they try to define model transformations. As such, ATL code tends to be always structured in the same way. So you know you want to transform a model element, you write a rule, the from part is where you put the element that you want to transform, and the to part is where you put the resulting elements. Java doesn't have this kind of structure, right? Java has methods and Java has statements. And how you use your statements within your methods is completely up to you. You can mix transformation code within your method with other control flow and other things. So there's less of a strict structure in your Java code. Now, this isn't in and of itself a bad thing or a good thing for any of the languages. It's just something that's really different between the two languages. Yeah, it's a completely different, or it can be a completely different approach as to how you define your model transformations. And depending on the case, it can be an advantage or disadvantage. So if you just want to, if you know you want to map A to B, you're probably better off with just the ATL code because you know what you have to do. You write a rule, you put A there and B there, and then you're basically done. Whereas in Java, there's different approaches as to can actually achieve your transformation. This can also help in complex cases where you need to do complex selections or such things. In ATL, this might lead to some code duplications of your rules, and in Java, you might be able to avoid those. Okay, so in summary, for this study, we set out to find evidence for this set of claims about how easy it is to express model transformations in a model transformation language, and we were able to find evidence thereof with some caveats, right? And there's basically 3 points that I want you to take away from this. The first one is the complexity overhead in Java. We already saw that earlier. Between 40 to 45% of the complexity in your Java code is overhead. And the largest portion of that overhead nowadays is the tracing, which has its own implications, right? And the other big thing is the structure between the 2 languages, or the structure of the code of the 2 languages differs greatly, and that has its own set of implications for your transformations. Okay, concluding our work thus far and concluding my talk here, we identified that there exists a large number of claimed advantages and disadvantages for model transformation languages, and we've seen that there's little research being dedicated to substantiating those claims. To combat that, we started doing this for claims about how easy it is to express transformations in ATL compared to Java. And our first results show that there is some advantage, but the use case, for example, the type of transformation you want to do, the involved meta models, the need for tracing, has a large impact on how much of an advantage there really is. Okay, this concludes my talk, and thank you all for your attention.
Okay, thank you very much. Any immediate questions on this? So I have one. I mean, so the evaluation, I think, is pretty clear. So that makes sense to me. My question is more about the consequences, which I appreciate is not really what you researched, but so you identified a couple of areas where model transformations are, so basically where there's overhead in implementing model transformations in Java, mostly the tracing, as you said. So does that suggest that maybe the right way to do this is to try and improve the support for tracing specifically, maybe have dedicated libraries that support that?
Well,
maybe the tracing on the one hand and the linkage to the source and target language on the other hand, because I mean, I'm sure they go together, rather than the entire cycle essentially of the model transformation.
Well, it's one way to go about things, I guess. Well, if there's an easy way to define traces in Java, that would definitely help. I don't know if it's the only way you can go for, because also the structure between the languages that I've talked about also has some implications that in some cases are things that point toward using general purpose languages, and in some cases it's probably still easier, even with a tracing library, to do it in a model transformation language, just because the structure is so clear and so straightforward.
Yeah, I mean, it's also the question whether you can separate this aspect.
Definitely. I think there's some work with maybe Java annotations that I know of, but I don't know how, or annotations in general doesn't necessarily need to be Java. But I'm not sure about how well that works or where the maybe disadvantages of this approach are. But yes, in general, if you can abstract away tracing, that would definitely help your development in Java. I'm not sure if it will instantly provide you a language that's always better to use than a model transformation language, especially if you look at things that we didn't even consider, because ATL doesn't really have those, like bidirectionality, incrementality, and stuff like that.
Yeah. Okay, good point. Yeah. All right, cool. Thank you.
Okay, so.
Okay. Is there any other questions immediately?
Yeah, maybe a quick one, if I may. So I asked in the chat, what is this McCabe complexity? And Matthias T, he gave a definition. So I understand that is then something which is interesting for testing also. I think it's a number of independent paths through a control flow graph, I guess. So has this anything to do with computational complexity? Because when you just said complexity, my first intuition was this is about runtime. So it's not, I understand.
Well, I think there are some implications, right? So a higher, well, I'm not sure. So a higher McCabe complexity will point to more, or would suggest more if statements, for example, since that splits your control flow. And checking those does require some computational overhead, but I'm not an expert in how much that actually impacts that.
Obviously, I can write, even with many if statements, very fast programs, and then others with few if statements, which are magnitude slower. So I just wanted to be clear, this is one of these, I mean, you talk about, you know, perhaps my intuition is the model transformation community, you know, looking at things from the inside. If you just say complexity, my first inclination would be, oh, he's talking about runtime complexity. Okay, this is probably what people from programming languages would first think of. So I think even when you have talked, one can see perhaps it's important to to have the same level of understanding.
Yes, definitely. Context is important, and properly discussing what you're actually trying to convey is also important. Totally agree.
And I also fully agree that this is related to quality and testing, because you have these independent paths, and there are empirical research studies which did show that there is a correlation between high cyclomatic complexity and error proneness. So it's easier to make bugs or write bugs, but it's not related at all to this computational complexity. But it's still important.
I didn't want to doubt the importance of that notion, but it's important to have the context.
It's definitely important to differentiate. So what we looked at was more the engineering aspect and the software engineering aspect, and less the performance and runtime aspect of the whole thing.
Okay, excellent. Thank you very much. So, thanks again, Stefan. And I think we move over then to Raffaela. Just to say, in terms of timing, I mean, we took a bit longer now than 30 minutes. I mean, because of the discussion.
Sorry about that.
No. I mean, you were perfectly on time. So it was not your fault. But we took a bit longer in discussion, which is okay. There's no problem with that. But just to say that, Raffaela, you've got 30 minutes as well. Yeah, so we won't cut you off at the top of the hour. Yeah, so you do your presentation as you planned, and then we still have time for discussion afterwards. Yeah.
Okay.
So please go ahead.
No. Okay. Hello, I'm Raffaela Groner, and first of all, I would like to thank you for inviting me to present you our research. And also thank you for listening to my talk, in which I will present you our results regarding performance engineering of model transformations, which is a joint work of several researchers from the University of Ulm and the University of Stuttgart. And I would like to start my presentation with a short motivation. If we write a program in a general purpose language like Java and we face any performance issues, it is a given to us that there are many different tools that can help us to analyze our program and pinpoint the causes of a performance issue. And all these tools have one thing in common. All of them implement the application performance management cycle. This cycle consists of 4 activities. Data is collected during the execution of a program. Then this data is analyzed. The analysis results are visualized. And at last, we can interpret these visualizations in order to find the cause of a performance issue and hopefully resolve it. I would like to remark one thing. Since performance engineering is such a broad field, if I now talk about performance engineering, I mean especially the application of this cycle. And as I already said in the motivation, for general purpose languages, there are many tools which already provide this cycle. And we are interested in how this cycle is applied in the context of model transformation languages. And if we take a look at the current research in the context of performance and the performance of transformations, we can see that there are many works focusing on the performance of the transformation engine. For example, they try to improve the algorithms inside the engine, or they provide concepts like parallel or distributed execution of transformation rules. Then there are also works focusing on how to improve the definition of your transformation scripts in order to speed up their execution. And then there are also some studies, but these studies focus more on how efficient model-driven development is compared to code-centric development. So in our research, we focus on how do transformation developers currently deal with performance issues. And in my presentation, I will present you 5 different parts about this question. We conducted a study to answer this question, and therefore I present you some demographics of the participants. I show you whether performance is relevant for model transformations or not. I show you some examples for strategies used in the context of model transformations and their performance. Also some examples for solutions and the corresponding causes these solutions resolve. And at last, some examples of how the study participants deem to be important to understand or improve the performance of the transformations. And in the second part, I would like to answer the question, how can we realize performance engineering for model transformations? And in this part, I will present you our profiler, which is a first step to realize the application of this performance management cycle also for model transformation languages. So let's start with the first part and our study. We conducted a mixed method study consisting of a quantitative online survey and a qualitative interview study. We used the results of the online survey to get an overview of the participants and get more knowledge about whether performance is relevant or not in the context of model transformations. And we used the interviews to get more insights on how the developers deal with performance issues. And we started our study by searching for potential participants. Here we use techniques from systematic literature reviews. Here we queried ACM and IEEE digital library for publications about ATL, Henshin, QBTO, and Viatra. Then we filtered the found publications using inclusion and exclusion criteria we have defined. And then we extracted the authors of the included publications and invited them to participate in our study, resulting in 653 potential participants. Then our questionnaire was fully answered by 84 participants. And based on the answers to the questionnaire, we invited some of the participants to our semi-structured interviews, resulting in 13 interviews with 14 interviewees. One interview was a group interview. And before I present now the results of our study, I have to remark 2 things. First of all, please keep in mind that our results do not address a specific transformation language. And the other thing is, which is quite interesting, in the interviews, we could identify 3 different types of interviewees. There are the pure users for whom the transformation engine is a black box. Then there are users with limited knowledge of the engine. And at last, there are the engine experts who have deeper knowledge about the engine, or they were also involved in the development in an engine. And in the following, I will use the abbreviations P, L, and E in order to indicate from what type of interviewee a statement is resulting from. And now let's take a look at the results of our study. And first of all, the demographics of the participants. And here we can see that the study participants use a wide range of different languages. So this also shows that our results are not really tailored to one specific language. So now let's take a look on whether performance of model transformations is relevant or not. And for this, we asked the study participants how often they are satisfied with the execution time of their transformations. And luckily, no one is never not satisfied, but there's also only 13 participants who are always satisfied. Then there's a huge group of participants who are often satisfied. And then there's also a huge group of participants who are just sometimes or only rarely satisfied. And we asked the participants about the reasons for their dissatisfaction. And here 30 answered that the execution time takes too long. 25 answered that the execution time fluctuates, for example, on the input models used. And 10 gave both as a reason. Some participants gave further reasons, for example, that the transformation engine typically does not optimize the execution of a transformation script in the best way, or that a transformation script is not defined in the best way. Then also scalability issues when using large models were mentioned, as well as the consumption of too many resources. Then also based on the results of our questionnaire, we could see that over 50% of the participants have already tried to analyze or improve the performance of their transformations. And also 57% of the participants rated it at least moderately important that the execution of the transformation does not exceed a certain execution time in the average case. The worst case is rated at least moderately important by fewer participants, but this might change due to the increasing usage of models at runtime. We also used the results of our questionnaire to conduct a hypothesis test in order to compare the participants who have already tried to analyze or improve the performance and those who have not. And based on the results, we can say that participants who have already tried to analyze or improve the performance tend to have more knowledge about the engine, are less satisfied with the execution time, they use larger models, and for them, it's more important that a certain execution time is not exceeded in their average case. So now we have also seen that at least a number of developers really care about the performance of their transformations. And now we are interested in the strategies they use. And here we could identify two different types of strategies applied. On the one hand, there are strategies used to prevent performance issues. And at the other hand, there are strategies used to find causes for performance issues. And for both types, I will now present you one or two examples. And we start with strategies used to prevent performance issues. And here, classically, performance tests are carried out. We could here identify various degrees of how systematically they are carried out. But this is not really the interesting part. The interesting part is that you have to solve two issues in order to carry out performance tests. On the one hand, you need suitable input models. And at the other hand, you need a suitable infrastructure to carry out your performance tests. And at the moment, both issues are solved mainly manually and with a lot of effort. So there's no really any support which can help you to carry out performance tests easily. Then let's take a look at strategies to find causes of performance issues. And one I would like to present you is the trial and error strategy. This one was only used by pure users. And if we take a look at their statements, it becomes clear why. They had no way to get any information on how their transformation is executed, and therefore the only thing left was trial and error. Then another strategy to find causes of performance issues we called test cases strategy. Here I present you an example from an engine user with limited knowledge of the engine. This interviewee collected information at the transformation level, collected information about the execution at the transformation level using log statements. And he also extended the transformation engine with log statements. And he also used a Java profiler to collect information. Then he changed manually the transformation rule used or the input model used in order to test the impact of these changes and therefore analyze the performance of his transformation. And he also carried out performance tests for which he mainly manually graded all combinations of possible elementary cases of input models. Here again, we can see that there's a lot of manual work to do in order to analyze the performance of your transformations at the moment. So now let's take a look at some examples for solutions and the corresponding causes they resolve. In the study, we could see that the solutions are either applied at the engine level, the transformation level, or at the model level. And there's also a set of alternative solutions. And now I will present you some examples for solutions applied at the transformation level or at the model level, because those are the interesting ones, because those can not only be applied by engine experts, but also by pure users. So let's take a look at solutions at the transformation level. Some transformation languages offer the concept of caching, which can be used to cache the results of very time-consuming calculations. And this can resolve performance issues caused by very expensive expressions, like the OCL expressions, all instances. Here, one ATL user reported in the interview that he often sees an ATL transformation that this concept of caching is not optimally used. And if you face any performance issues, you have to manually extract the parts you want to cache, and therefore update your script again manually to improve the performance. Another way to solve performance issues is the usage of refactorings. For some data types, some transformation engines try to avoid side effects by copying whole lists and then add a new element. And this copy operations inside the engine can be really, really expensive. And one can avoid these copy operations if one changes the data type. But here again, you not only have to manually change your your transformation script and change the data type, you also need the knowledge to know which data type is better suited for your issue. Then let's take a look at a solution at the model level, and this one is quite an interesting one. Here, one of the interview had a transformation which had to defer many different cases during the execution of his transformation. And his solution was to define a new transformation, a kind of pre-transformation, which simplified his input model. And so his main transformation had to consider fewer cases, and was therefore afterwards faster. So now we have also seen some examples for solutions used in the context of model transformations. And now let's take a look at what transformation developers think can help them to understand and improve the performance. And here we could identify various types of different help they would like. First of all, they want more information about the structure of their models, like the average number and variance of references, or also the number of model elements inside their models. They also desire more traceability information, like the traceability between the input model and the output model, as well as between the input model and the transformation rule applied. Then, of course, they want more information about the execution of the transformation. Here, for some examples, they want more information about the number of investigated model elements, the number of applied rules, and also the execution time for each rule, which is quite a natural metric for measuring the performance. Besides more information, the study participants also want more tool support, like profilers at the transformation level, or also analysis that help them to detect expensive operations or patterns inside their transformations, or also analysis that provide improvement proposals, like how can I optimize the call order of my transformation rules. So now this was the first part of my presentation. Now let's take a look at the second one, where we look at the question, how can we realize performance engineering for model transformations? In the first part, we have seen that this performance management cycle is mainly applied manually at the moment. And our attempt to help developers to apply this cycle more comfortable is our profiler for the declarative transformation language engine, which is presented in a tool demo and also described in a tool paper. And now I'll show you a selection of visualizations our profiler provides. We have two different types of visualizations. One visualization gives an overview of the execution of the whole transformation script. And then there are some visualizations that present informations about a single execution of a transformation rule. But before I present you some visualizations, I will present a running example and explain a little bit more concepts about Händchen. And our running example consists of a meta model, which describes a program in an imperative programming language. And so expressions like this one at the top is presented in our model, like here at the bottom. And our transformation rule implements the compiler optimization constant folding, which means our transformation looks for expressions like this one and replace it with its result. And since we want to replace all such expressions in our input model, we call a so-called loop unit called apply constant folding. A loop unit is a control structure in Händchen which applies a transformation rule as often as possible. Händchen offers many different control structures like sequential application of transformation rule or conditional application of transformation rules. So now if we apply the transformation rule constant folding to a model, what happens? In the first step, the engine orders the nodes from the transformation rule, which is also called the search plan, and it determines all possible candidates for each node in the transformation rule from the input model. Then the so-called matching process starts. This means the engine takes one of the model elements from the candidates for a node and checks whether this model element fulfills all constraints the node have defined. And if this is the case, the model element is bound to the node. If we now take a look at our transformation rule, we can see that binary should be referenced by an expression. The engine uses this information and also restricts the candidates of the affected nodes. Then the matching process continues. If one model element, for a node, no model element can be bound, the engine uses a concept called backtracking. This means the engine goes one step back in the search plan. It revokes the latest binding and all restriction this binding caused, and then the engine tries to find a new binding for the node. And this is the way the matching process works. And this will continue until a match was found and the transformation rule can be applied, or until no match could be found and then the application of the transformation rule fails. So now I have presented you all details about Händchen, and now let's take a look at the visualizations our profiler provides. And the first one I would like to show you is the overview visualization called the Callcraft. This visualization shows the total execution time in milliseconds, and for each transformation rule and unit call the execution time in milliseconds, and the color indicates also the execution time according to the heat scale on the right. So now if you want more information about the matching process of a single rule, our profiler offers some other more detailed visualizations, and here I present you two of them. The first one is the backtracking graph. This visualization shows at the x-axis the nodes from the transformation rule in search plan order from left to right, and at the y-axis the number of revoked bindings. And here we can see that over 600 times a binding for the nodes binary left and right were revoked. And we can also see that 300 times a binding for the node left and was revoked. This huge number of backtracking, of course, has an influence on the number of investigated model elements. And more details about this can be seen in our model elements graph. This visualization shows at the y-axis from top to bottom, again, the nodes from the transformation rule in search plan order. And in each rectangle, the number at the bottom left indicates the number of investigated model elements during the matching process. And the number at the bottom right indicates the number of candidates available at the beginning of the matching process. And the percentage above is the ratio between these two values. And here we can see the impact of these huge numbers of backtracking, because for left end and right end, we have to investigate many, many model elements until a match was found. How can we explain this now in more detail? If we take a look back at the backtracking graph, we can see that for left end, 300 times the binding was revoked. which also means 300 times all available candidates for right-int were investigated until a match was found. And much more critical, if we take a look at the node right here, 624 times a found binding was revoked, which also means 624 times all available candidates for the node left-int were investigated until a match was found. So you can see only with these two visualizations, we can already explain in more detail what happens during the execution of our transformation rule. And this is also all I would like to present you from our profiler, and now I would like to summarize my presentation. First, I presented you some demographics about our study participants and whether performance of transformations is relevant or not. And these results are also published in our paper, A Survey on the Relevance of Model Transformations. And also, we published the corresponding data in an open access repository. Then I presented you some examples for strategies and also solutions applied in the context of the performance of model transformations. And these results are also published in our paper, An Exploratory Study on Performance Engineering in Model Transformations. And again, we also published the corresponding data in an open access repository. And at last, I presented you some examples for help that study participants deem to be important in order to understand and improve the performance of their transformations. And I showed you some examples from the visualizations our profiler offers. And this profiler is also presented in our tool paper. And with this, I'm at the end of my presentation. Thank you for your attention, and I look forward to your questions and a nice discussion.
Okay, thank you very much. Thanks, Raffaela. Sorry, I cannot see. Let me just see if I can see all the participants here at the same time to see if anyone has a question. But maybe I just start. So I like the fact that you did some well, how do you call it? Some focus group analysis before you started implementing your profiler to basically understand what people actually want. So that is certainly a good idea, and I don't think that happens very often. So the natural thing after that wouldn't it be to basically take the profiler once you've implemented it, go back to those people and try and find out if this is if they can give you feedback on it or what they think about the features that you implemented there. So did you manage to do that, or is that possible to do?
We didn't evaluate the profiler with the same people, but we evaluated the profiler in the context of a master thesis. But it was a really small study with 5 participants. Mm-hmm. And here the result also was that the profiler is usable and also and helpful. And also some of the participants could also not only identify the cause of a performance issue, but also came up with a solution of the issue.
Mm-hmm. So by which criteria would you evaluate the profiler? Just in terms of how much information it gives you, and if it gives you the right information, or how helpful it is to actually write better transformations that are more performant, or what is the kind of target there?
We evaluated whether it helps to understand the execution of the transformation at first. So we had 3 example transformations would all have some built-in performance issue, more or less. And then the study participants had to analyze each example and explain what they see, what they think, what the visualizations show them.
Mm-hmm. Okay. And do you want to say what the results were, or if you...
Okay. The result was sorry. The result was that all of them could explain what happens based on the visualizations correctly. Mm-hmm. And also, I think 3 of the 5 were also able, based on the information they got from the visualizations, to propose a solution for the built-in performance issue.
Okay. Yeah, that was my second idea, I suppose. If it helps to improve the transformations rather than just telling you where they are good or bad or something like that, or where you lose your performance. Okay, interesting. Thanks. So any other questions? I mean, Matthias was busy in the meantime posting lots of Stefan was that Stefan? Sorry. Well, all of them. So people are busy posting references and papers here, including, I think, some of those that you mentioned. So that will be useful if we want to follow this up. If you have any questions, please put them in the chat or raise your hand, but I need to find out how to show everyone on my screen so I can actually see you. So sorry, I need to go to gallery view, I think. Oh yeah, here we go.
I can't see how to raise my hand. Can I ask a question like just
You can just wave at us.
Okay, so if I may, yeah, I think this profiling is interesting to see the performance of, transformation procedure or module or whatever on a given model, both maybe for the transformation designer and perhaps even for the engine designer. But I have a question. You also mentioned execution time, so I'm coming back to that one. Is there also work, are you aware of work where you try to prove things maybe empirically, like my transformation program here or transformation procedure runs in quadratic time, right? So to do that by benchmarking, of course, I guess an issue is you would need a lot of input models which grow in size, and then for each one take the execution time. So then I imagine how do you do that to, if not randomly, which may be a problem with the output, produce larger and larger models on which you actually can benchmark your transformation procedure?
Yeah, there are multiple questions inside this, so I try to.
Yeah, sorry, I think you get the direction. It's more than going away from individual transformations to you have a transformation program and you want to make a statement not about a concrete model, how it performs, but really on a class of models, and adapting this traditional view, we measure running time in terms of the input size. And input, of course, will, I assume, at least are models. So.
So it's not the focus on my further research, but I agree it's really hard to create also a comparable benchmark, especially with increasing size of the input models. There's also an additional line of research only focusing on how to generate models. And here we already have the issue, are generated models enough? Do they also need to have more realistic, how should I say? Should the model always be realistic, or generated models enough? That's already an issue. And this was also an issue by the interviewees mentioned who carried out performance tests. Even for just simple performance tests, they don't have enough models. So this is already a large issue before one can tackle such an issue at all.
Yeah. So, I mean, we did a little bit, it's, I think, related on a graph transformation language, GP2, and to do this benchmarking. So what we did is to simplify things, look at different, so our inputs are graphs, just graphs. So we looked at particular graph classes where it's relatively easy to generate larger and larger graphs, like let's say complete binary trees, right? So you have a clear shape and okay, this is level 1, you add another level, that's the next larger tree, and so on and so on. And so you can relatively easily write a generator, or let's say a cycle graph or stuff like that. But in the case of models, at least I wouldn't have an initial idea how to do something similar, right?
Maybe to add to that, there is work by the group of Daniel Varro, which developed some sort of a generator for realistic models, or at least those which also satisfies OCL constraints and so forth. So that could be a good way forward, because it's interesting, as you mentioned, like it's not the size, it's also the structures of the models or graphs involved, which have a deep impact on performance.
Yeah, but it's even more varied than in the case of graphs. Even for graphs, you have already, of the same size, you can have, as you know, a completely different shapes. But then with model, it's much more what is in there, I think, in general. So, one could, of course, take the standpoint, I just generate something randomly of some size, but I doubt that is really meaningful in the case of models. Okay, thanks.
Okay, excellent. So, unless there are any more urgent questions of sort of a general nature, I would close the session here, and we can all stay here and continue discussing sort of more informally, but we would close the Zoom link, so we are a bit more amongst ourselves. So let me thank again Raffaela and Stefan for their nice presentations, and everyone else for listening, and we all see you again in 2 weeks with what, Nick? So what was...
we have an experiment with 3 talks in 1 hour with our own communities, Berthold, Hoffmann, Frank Dreves, and my God, I've got the third, sorry. About
one talk with 3 authors.
Sorry, it's on the webpage, yes. Yeah.
Okay.
So,
okay. Excellent.
Yes. So if anybody is still on YouTube, you can still join us. I just stopped the YouTube live stream now. So also thanks a lot to Raffaela and Stefan from my side. And again, like everybody who's currently on the Zoom can just stay. I'm only gonna switch out the YouTube live stream.